Hello students, in the series of lectures in the subject vlsi design, today we are starting with interconnects, and more specifically we are starting with interconnect modeling. Okay. So whatever chips we fabricate in VLSI design, most of the area of the chips is made up of wires. Okay. So these wires are called interconnects. Okay. Because the transistor's size is very small. Okay. The maximum chip area is covered with the wires. So these wires are called interconnects. So their modeling is of very much importance. Okay. So for example, let us take a CMOS inverter. So this is the CMOS inverter. Okay. So if we want to draw the layout of CMOS inverter, then we can draw a diffusion line analogous to the NMOS and diffusion line with dotted analogous to the PMOS like this. So we are drawing diffusion lines here for PMOS and diffusion line for NMOS. Because there is a connection between these two diffusion lines, so a connection is made here by defining the cross sign. This is the interconnection that is mentioned. Now two lines are drawn here for supply and ground. So for supply this is the line, for ground this is the line. Okay. And again there are interconnections here and here. So these are the interconnections. So these interconnections are again made with cross. Now for the purpose of making the your gate terminals, so polysilicon lines are drawn. Okay. So one polysilicon line here and one polysilicon line here. So it will be connected to the input A, okay, like this. And from here we are using a metal wire to the output F. Okay. So this particular diagram that we have made is known as layout of MOS inverter. Okay. Now as we know these widths and all dimensions of this layout by using layout design rules, so we does not need these type of structures. So a very simple structure can be made with the help of the layout. So this structure is made by simply drawing the sticks like lines here, and this particular diagram is known as stick diagram. Okay. So here you can see that lot of wires are there. Okay, in this particular design. Okay. So wires are basically very important in VLSI design because they determine the speed, power and noise. Okay. And also they decide about the delay. Okay. Now let us come to the wire geometry. Now suppose we have two wires that are connected, that are laid on the surface. Okay, this is the surface on which these two wires are laid parallel. Okay. Now let L is the length of wire, W is the width of wire, and T is the thickness of wire. And another wire that is being placed parallel to the first wire is placed at a distance S from the wire. So we define a parameter called pitch. Okay, so pitch is nothing but the sum of width of wire and the distance the second wire is placed from the first wire. Okay, so pitch is defined as W plus S. So what is the importance of the pitch? Suppose we want to draw 10 parallel wires. We want to place 10 parallel wires here like this. Okay. So how much spacing is required in order to place these 10 wires? So this is the pitch. Okay. So if we place one wire here, okay, the amount of spacing will be W plus S. Then second wire will be placed and amount of spacing will be again W plus S. So if 10 wires are placed parallel, then the amount of spacing is 10 times W plus S. Okay, so with the help of pitch, we can determine the spacing that is required depending upon the number of wires we are placing. Okay. Next, geometrical consideration, we define a term that is known as aspect ratio. Aspect ratio. So aspect ratio is nothing but the ratio of thickness of wire to the width of wire. Okay, D upon W. In older VLSI processes, this aspect ratio was kept less than 1. But in modern processes, the aspect ratio around 2 is maintained. Means that the thickness of the wire is 2 times the width of wire. Okay. Now let us consider another parameter known as the wire resistance. Now what is wire resistance? So we all know that if we have a wire of dimensions width W, length L and thickness T, then we can define the resistance of wire as R equals to rho L upon A, okay, where A is the area of cross section of the wire. Now what will be A? That will be W times T. So if I arrange this equation like this, means rho upon T is kept here, and this is L upon W here. Okay. So this particular term rho upon T is defined by R square or R box. So this is the resistance that is defined and is equal to rho upon T, where rho is the resistivity of the material of wire and T is the thickness of wire. Okay. The unit of this resistance is ohm per square or ohm per bracket. We can define it as ohm per bracket is the unit. Okay. R box or R square resistance is also called sheet resistance. This is also called sheet resistance. Okay. Now, what does it mean actually? So R box basically is the resistance of the region having same dimensions, means same length and same width. The length is W and width is also W. Okay. So if this is the portion, then the resistance of this portion is defined as the R R square. Okay. So now let us take an example of this in order to understand this. Now suppose we have a wire of length L and width W. Okay. So the idea is that, let's say, this is divided into four sheet resistances. Means this is the square, this is the square, this is the square, and this is the square. So the resistance of the complete wire can be defined as 4 times of R in this particular R sheet, R bracket. So this is the overall resistance of the wire. Okay. Now, how will you calculate the number of squares? So in order to find the resistance of the wire, you can use the formula R equal to R square multiplied by number of squares. So how you will calculate number of squares? Okay. So now for that matter, let us suppose that this is the length of wire, this is the width of wire. So what will be the area of the wire? The area of the wire will be L times W. Okay. Now area of one square is what? Area of one square is what? Means it has the length W and width also W. The area of the square is nothing but W into W. Okay. So number of square is nothing but LW upon WW. That is your number of squares. Okay. So that will come out to be L upon W. Okay. So L upon W is the number of squares in this particular wire of length L and width W. Okay. Now we need to find the overall resistance of the wire. So we can use the formula that resistance of wire is equal to R square multiplied by number of squares. So R square is denoted by this. This is multiplied by number of squares, and number of squares is nothing but L upon W. So this is the resistance of the wire that we can calculate. Now comes the choice of metals. So until 180 nanometer technology, aluminum was the first choice. Okay, and most wires were made of aluminum. Now modern processes basically often uses copper, but there is one disadvantage associated with copper, and the disadvantage is that copper atoms basically tend to diffuse into the silicon, and they can damage FET, field effect transistor device. Okay. So this is the choice of metals. Now the contacts that we made while we were drawing the stick diagram, we made some contacts. Okay, so these are the contacts that we made. So these contacts also have some small resistance. Okay, so what is that resistance? that we will discuss. So contacts have a resistance of 2 to 20 ohm respectively. Okay. Now comes the wire capacitance. Okay. So wire has capacitance per unit length. Wires basically have capacitance per unit length. If we have longer wire, the value of capacitance will be high. Okay. So let us consider a side view of the wires. Okay. So in this diagram that you can see, this is one wire, this is another wire, this is third wire, and these are the layers. So this is the first layer. Let's say the layer above these wires is this, and layer below this wire is this. So what are the capacitances that will be there? So there will be two capacitances that are adjacent capacitances between the two wires. So these are the adjacent capacitances. ADJ, CAD. This will again be CADU. Now another two capacitances will be associated with the layers above this layer and layer below this layer, middle layer. So the above top capacitor is C top and the bottom capacitor is C pot. Okay. So now what will be the total capacitance? So total capacitance will be the sum of C top, C bottom and 2 times 2 times the adjacent capacitance. Okay. Now this you have already known. The equation of capacitance is epsilon A upon T, and epsilon is equal to K times epsilon naught. The value of K for silicon is 3.9. Value of epsilon naught is 8 into 8 6 10 raised to the power minus 12 farad per centimeter farad per meter and minus 14 farad per your centimeter. Okay. Now let's say you are driving one inverter with the help of another inverter. Okay. So this is the stick diagram. On the left side, you can see the stick diagram of this CMOS inverter. On the right side, you can see the stick diagram of this CMOS inverter. Okay. Now, the output of first inverter is the input of second inverter. So you need to connect this point, the output point of first inverter, to the input of second inverter. Okay. So remember, this line is a polysilicon line. Okay. This particular line is a metal line. Okay. So wherever there is a contact of polysilicon and metal and polysilicon, so there would be some resistance also there. Okay. So there are two ways to connect the these output of one to the input of another. The one method is that we can use metal lines. Okay, there is metal line. So one metal line we can draw and we can connect it here and we can connect it here. Okay. Another approach is we can also use polysilicon line. So if you use polysilicon line, then you don't need contact at this point. Why? Because this line is already a polysilicon line. Okay, so nothing worse will happen. Now there will only be one interconnection, that is this. Okay, There is no need to interconnect this, because as we increase the number of interconnections, so interconnections basically require some area on the chip. Okay, so more number of interconnects, more number of contacts will basically occupy more area. Okay, so that's why polysilicon line is preferred here. Okay, so occasionally polysilicon lines can also be used. Now let us consider one numerical. So this is a simple numerical, you can see. So calculate the sheet resistance of a zero point 0.2 micrometer thick copper wire. So the thickness of copper wire is given, that is 0.22 micrometer. T value is given here. Here you have given T. Now the resistivity of copper is also given, that is 2.2 times 10 to the power minus 8. So how sheet resistance will be find out? You can easily find it by using the formula rho upon tau. So sheet resistance will be zero point 0.1 ohm per square. Now we need to calculate the overall resistance of the wire. So the overall resistance of the wire will be R square multiplied by number of squares. So what are number of squares? That are L upon W, that we have already discussed. So what is the length of wire? The length of wire is what? 1 mm. And what is the width of wire? That is 0.125 micrometer. So you can just put these values in this equation and you will finally get the resistance, that is equal to 800 ohm. Okay, so this is how you can calculate it.